In this lesson, we're going to learn how to graph velocity time graphs when we're given a position time graph. So first, let's remember that slope is rise over run. And because time moves on towards the right in our position time graphs, run is always going to be positive. Rise, however, can be positive if the graph is going up or negative if the graph is going down. Recall that a graph that looks like that has a positive slope, one that goes down like that has a negative slope, one that's horizontal has a slope of 0, and one that's vertical has a slope that's undefined. Also remember that we've seen that on a position time graph, the velocity is given by the slope. Slope indicates velocity on a position time graph. And now that we've introduced velocity time graphs, where velocity is on the vertical or the y-axis, we know that on those, velocity is just given by the y value. So to take a position time graph and make a velocity time graph for the same object, for the same motion, our task is to take the slope at any time on the position time graph and turn it into the y value at any time on the corresponding velocity time graph. So here's an example of a position time graph that we've seen before. Let's say we wanted to figure out what the y value was on the velocity time graph at the time 1 second. We would go to the 1 second mark here. We would draw ourselves a tangent, which I'm going to draw just below the line for clarity, but really it's on the line. And I would ask myself, okay, what's the slope of that tangent? And the slope of that tangent would become the y value of the velocity time graph that I'm going to graph below at 1 second. So that slope would become the y value below. And then to get the next y value, let's say I wanted to do at 2 seconds, I would repeat the process and repeat the process and repeat the process at every time. And I'm just choosing seconds, but I could be going in between them as well. And then I'd do the same everywhere else. Now that seems really tedious, but remember that in graphs like this position time graph where we have straight lines, we've seen that that indicates uniform motion or constant velocity. If the slope of the position time graph isn't changing during a given time interval, then we have uniform motion or constant velocity. And that means that the y values of the corresponding velocity time graph aren't going to change during that time interval either. And that's going to save us a lot of work, because instead of having to find all of these slopes for each individual tangent, I just find the slope for the overall line segments, and then those become the unchanging y values for those same times on the corresponding velocity time graph. So for example, the slope of this line, well, it goes from -6 to +8 over 7 seconds. So that's 8 minus -6. 8 minus -6 divided by 7 is +2. So the slope here is +2 meters per second. And I'm going to use positive as the defined direction of right. Therefore, negative would indicate left. Here, there's no rise at all. The rise is 0, so the slope is 0, or 0 meters per second. And here we're going down 10 in a time of 8 seconds. So 10 divided by 8 is 1.25, and it's negative, so the slope is negative 1.25 meters per second. Again, that's negative 10 divided by 8. So now that I've got that, those slopes, which are the slopes for each individual tangent point, any of these have a slope of 2. If I were to draw tangents here, they would all have a slope of 0. Any of these tangents would all have a slope of negative 1.25. They become the y values down here. So for the first 7 seconds, I have a slope of 2. All of these y values have to be equal to 2. For the time between 7 seconds and 12 seconds, all of those tangents had a slope of 0, so all of these y values have to be 0. And from 12 to 20 seconds, all of the slopes were negative 1.25, so all of these y values have to be negative 1.25. Now what about the connections between here? Well, if you look above, what's happening is the slope is changing instantaneously. We've got a sharp bend there. So that means that the slope here is, the y values here are changing instantaneously as well. So we just draw a vertical line like that, and those should connect, like so. So this is now the velocity time graph for this position time graph. Okay, now let's look at an example where the slope changes continuously on the position time graph. In other words, where the position time graph is curved. And this is more difficult, and the best we're going to be able to do under these circumstances is just kind of estimate. But here is an example of a position time graph like that. Now we're going to follow the same process that we did before, where we want to know the value of the slope at each point on the position time graph, and those are going to become the y values below. Notice here I've taken all labeling off the axes because we're just going to be estimating. Let me show you an illustration of a graph that looks a bit like this so that we can see what the tangents are doing. The purple line is the tangent. It starts out positive. It gets less positive until it becomes 0, and now it's pointing downwards, negative. It becomes more and more negative, more and more downward pointing until it starts becoming more upward pointing, in other words, less negative, 0 at the bottom, and now it's positive again, getting more and more positive until the end. Let's watch that one more time. We see a positive slope at the start, becoming less positive until it becomes 0 at the top. Now it's a negative slope, becoming most negative in the middle there, now less negative, less downward pointing, becomes 0 again at the bottom, and then positive. Coming back to this graph then, the easiest place to start is the places where the graph has a horizontal tangent. So that's here where it has a 0 slope, and here where it has a 0 slope. Over here, these slopes are all positive, going from more positive over here to less positive as we approach 0. The slopes in between here are all negative. It's a bit less negative, then it gets more negative, more downward pointing, and then less again, until it becomes 0, and then over here they're positive again. First less, and then more, and at the end it's maybe about the same as it was just to the left. Now all of those slopes we're going to transfer to the y values. I'm going to zoom out a bit so that we can put these both together. Now, the easiest thing, as we just did there, is to always start with the places where the position time graph has a horizontal tangent, because those are going to be y values of 0 or x-intercepts on the velocity time graph. So if I imagine dropping down into this graph that's lined up below, I'm going to have x-intercepts here and here. And I know that I need more positive y values and then less positive y values on the velocity time graph because I had more positive and less positive slopes up here. So we don't know exactly what that's going to look like, but this would fit the bill, more positive to less positive y values. Then I have negative y values because up here I have negative slopes that go from less negative to more negative, meaning they go downwards until they become less negative again, and then become 0 here. And I could draw this a bit nicer, make that a bit more curved, like let's say that. And then they become positive, going from less positive to more positive. And if they really do become the same slopes above, then we should get the same y values, and it should start to become horizontal. Kind of hard to tell what's going on there. So this is just a bit of a guess. By the way, this is called graphing the derivative of a function. You'll learn all about this in calculus, but you'll have a head start now. One last thing to point out is that notice that here we were only interested in the slope. We weren't interested in the y value at all. So this graph here is the same position time graph as this, just vertically shifted downwards. All the slopes here are the same as here, but the y values are different. If the slopes are all the same for this position time graph, then its velocity time graph would be the same as well. In other words, both this position time graph and this position time graph would have the same velocity time graph. Only the slopes on the position time graph matter. Okay, so that's an introduction to graphing velocity time graphs when you're given a position time graph.